Hi, good morning everyone. My name is Peter Ramsner.
Hi, my name is Ulama Awamba.
My name is Chichukuka Monu.
And my name is Sameka.
So today we'll be sharing our senior design project review. We'll first look at the problem that we're trying to address, the solution that we generated, how we implemented that solution, but most importantly, how we evaluated that solution to make sure it solved the problem at hand. We'll then wrap it up with a recap of our learning experience, and then field any questions you guys may have. So in this project, we were trying to address the problem of runoff road accidents. These accidents account for 1,550 deaths every year and 71,000 injuries every year. And these accidents are usually caused by either drunk driving, tiredness, or just plain old carelessness. So to address this problem, we designed a lane departure warning system that would provide a quick and effective alert to the driver once there was lane drift. We subdivided this system into three main design components. The input. How will the system monitor the driving environment? The control unit. How will the system interpret that input data to decide whether or not there was lane drift? And then the output. How will it alert the driver once there was lane drift? Additionally, we considered some benchmark performance criteria. The system had to alert the driver within 1 second of the drift. The system should not alert the driver once the turn signals were activated. And the system should be functional for different types of lane markings. So it would work for a solid or dash lane marking. It would work for a single line or double line lane marking, and it would work for a yellow or white lane marking. Moreover, the system should perform a safety self-check test. So before the car started moving, the system would ensure that all its components were functional. The system would also adhere to some specific safety and electrical requirements put forward by the National Highway Traffic Safety Administration and the Society of Automotive Engineers. We used all this criteria to generate our solution. I'll now hand over to Uzo to shed some more light on our solution ideas.
So as Peter mentioned earlier, we divided our system into three main components: the inputs, the outputs, and the control unit. And we figured that the best way to come up with the ideal solution for our lane departure warning system would be to find the best solution for each of those components and put it together to make the holistic lane departure warning system. So for the input unit, we checked different technologies. We had the infrared technology and the camera technology. Now for the infrared technology, this just in a nutshell bombards the road with infrared rays and it gets reflected. Now we're leveraging the differences in wavelength between the white lane markings and the color of the asphalt, which is typically gray or black. And for the camera technology, just a vision-based system that's very forward-looking and takes real-time images of the driving environment and feeds this information to an image processing software. Now, this decision matrix you see was what influenced our choice of our input units. So as you can see here, we chose the infrared sensor. I'll just highlight quickly the key competencies of the infrared sensor over the camera. First of all, is the weather effects, the fact that it was more weather rugged and did not rely so much on image. And secondly was, we had a constraint on cost on this project, and the infrared technology was a lot cheaper and also giving us the desired result we wanted for the input. Secondly, we looked at the control units. So the control units, how do we interpret the data that comes from the driving environment? And we went to the market and evaluated a couple of options, including FPGA boards and mini processors. Now, the FPGA boards you can see there, we looked at the left FPGA, the basis, pattern, and black mini processor. Now, this decision matrix will just give you in a nutshell what influenced our decision on how to design or implement our control unit. We chose the basic system board. Key competencies: the processing speed of the basic system board was high enough to be able to transmit the output signal to the driver. And secondly, also the input-output component for connection with the FPGA board was, we had enough connection because, as you can imagine, this system has a lot of peripheral attachments to it. And another thing was power consumption. The power consumption of the basic system board was minimal, and so you do not have a significant power footprint on the battery of the car. And finally, we looked at the outputs. So how do you alert the driver effectively when you have a lane drift? And we evaluated LDWS vibrators and buzzers. Now, the three vibrators came out tops. primarily because of human interaction. We wanted to be able to give the driver a quick, speedy, effective alert. And the best way we could do this was physical, because again, as Peter described with run-off-road accidents, drowsiness or being tired or not being conscious of the environment, you may not be able to see an LED or hear any sound. So the vibrator came out to us in that regard. However, we figured that a combination of different alert systems would help to make our system more effective. So we chose two. We chose the LEDs as well. So in our final solution, for the input monitoring the driving environment, we use infrared technology to bombard the road with infrared rays and get reflections. For the control unit, we use the basic system for instance, an FPGA board. And for the output, we chose the option of seat vibrators and LEDs. Now I'll hand it back to Uche.
Thank you, Uzo. So Uzo showed you the final solution. Next, we had 9 weeks from then to come up with our prototype. And we set deliverables for each week, which we were supposed to meet at a given time. We were successfully able to do this with time and hard work. Then we decided to evaluate. We split our evaluation into expert opinion evaluation, simulation evaluation, and the prototype evaluation. Just like we said in the beginning, we split our whole system into the input, the control unit, and the output. So for the input, the camera came up with a glitch due to bad images in poor weather condition, and the sensor-based system actually won an AutoView won innovation prize. For the control unit, for our system, the FPGA board was better for the system we were planning to build. And for the output, you want contact with the driver so you can have quick response, and the vibrator and the LED were able to do this. Next, we use Xilinx and state padding Xilinx to come up with the states for the different scenarios. When you're in the middle, when you're on the right side, drifting, and when you're on the left side, drifting. And the different interactions with these scenarios, as you can see. We also use Model Sim to test 4 different scenarios when you have different color lane markings, whether it be white or yellow, and when you have dashed or straight lane markings. Our system was able to do this. We used the Model Sim to determine the incremental alert system. Our system gave us incremental alerts. We also checked the functionality of the turn signal. If the turn signal is on, our system doesn't perform. If it's off, our system works. And then response time, that's the time from the input to the control unit to the output, was 1.2 microseconds. That was a good time for us. We then had our prototype. And for the prototype, the key thing we were focusing on was testing it in different weather conditions. We decided to go with a base of 25 trials for each of these, testing spring, summer, fall, and winter. Spring and summer gave us the results of 23 to 24 out of the 25 trials we did, positive results. While the fall and winter, due to the leaves on the road or due to ice, had a bit of a glitch of 21 out of 25 and 22 out of 25 for the winter. Now I'll pass on to Emerson to do that.
Thank you, Jane. So I'm sure this is the part that everyone has been waiting for. This is a video showing a demonstration of our LDWS system. As you can see from here, it's not that clear, but these are the indicators which indicate when there is a drift. And these are the turn signals. So when they are pressed, it shows that the driver is trying to make an intentional drift. So now this is for the left lane drift. As you can see, the car, when it crosses the lane, the left LED comes up and the vibrators also make some noise. And as the extent of the drift increases, the vibrations also increase. This is the same for the right lane drift. When it crosses the line, you see the right LED comes up and the vibrations also go up. Now for the turn signal, when the driver puts the turn signal on, that shows that he's trying to make an intentional drift. And as you can see, when the car crosses the lane, none of the LEDs or vibrations come up. And lastly, we gave the driver the option of choosing between the LED or the vibrations. So in this case, for the left lane drift, he has the option of using the vibrations only. So only the vibrations, go up. And then for the right, when the car crosses the right lane drift, only the LED option goes up and the vibrations don't go up. As you can see here, just right LEDs go up. So that's just a recap of our project. We had a problem which we solved with the LDWS system. We also implemented it and evaluated it, as Uche mentioned. So what did we gain from this project? We were able to pull out all our knowledge and resources from classical like digital system design and senior design in implementing this design. We're also able to learn industry corporate standards while also being able to manage our deliverables. And we also understood the effects of team dynamics on our project progress. Acknowledgements, we we express our special thanks to the Department of Electrical and Computer Engineering. We also like to thank Tommy Igun, our corporate advisor, for encouraging and supporting us financially. We also like to thank our faculty advisor, Dr. Foster, who gave us, and Dr. Kim as well, who gave us fatherly advice on our project. At this point, we hope you enjoyed our presentation, and we thank you for listening to us, and we'll take any questions that you have. Okay, please.
Did you ever think about the possibility of a driver being tired and leaving the turn signal on and possibly drifting left and right?
I mean, that was one scenario that we did not consider. I mean, I think when you're looking at a human interacting with an electronic device, there's so many different ideas, so many different scenarios you can consider. And I think this system, accommodates the typical scenarios. So I mean, I'm sure there's like some like extremes on each side continuum that would break the system. But I mean, the system accommodates, I guess, 85 to 90% of the time.